So in the last video we talked about the curl. In this video we're going to talk about what we call the divergence. This is another operator on a vector field. So if we have f equals pi plus qj plus rk, the divergence is this expression. The divergence of f is the derivative of p with respect to x plus the derivative of q with respect to y plus the derivative of r with respect to z. Note here that unlike the curl, the divergence of a vector field is a scalar function. There are no vectors on this side of the expression. Also note that we can use our nabla that we were using before, the derivative with respect to x, I plus the derivative with respect to y, j plus the derivative with respect to z, k. If we were to take this thing and we take the dot product of it with f, now, no, this is just a pseudo vector. It's not really a vector, but using the same format that the dot product has, at least, then we can essentially say that we're taking the derivative with respect to x of p plus the derivative with respect to y of q plus the derivative with respect to z of r, and we get that scalar. That's exactly what our divergence is. So you can kind of think of this as kind of the opposite of the curl in a sense, where one is the cross product, one is the dot product. Note now that we have three operators that involve derivatives. We have the gradient, we have the curl, and we have the divergence. These are all derivatives in a sense, but they're all very different in the way that they're structured. So if we have all these operators, we have our notation here. We could say the grad of little f, or we can say nabla f. We have the curl of capital F, or nabla crossed with capital F. And now we have the divergence of f is nabla dotted with capital F. So very similar looking things, but we can distinguish between what goes into these operators and what comes out of those operators. With a gradient, we don't take the gradient of a vector field. We take the gradient of, you could say, a scalar function. This is a function of x and y, or x, y, and z, and what we get out is a new vector. With the curl, we put a vector field into it, and we get a brand new vector field out of it. So we actually don't change the type of object that we have by taking the curl. On the other hand, the divergence, we put a vector field in, and we get a scalar function out. Those are very different results from each of these. And it's good to keep in mind exactly what each operator is doing, what it can act on, and what it gives you. Another thing that we can note here, remember our definition for gradient, we used it both for 2 dimensions and 3 dimensions. In fact, it can work in any dimensions we want. We just, instead of having dx, dy, ddx, ddy, ddzd, we'd have maybe more components later on for the nabla that we have there. Maybe we have it if our fourth variable was maybe w, we'd have like a ddw times whatever our standard basis vector would be called in that case for the fourth component. I guess don't want to get too much into it than that. We'd have to actually give the notation there. But the point here is that this is pretty easily extendable. Same thing is actually true for the divergence. There's nothing stopping me from having a fourth component where I just add on that fourth component at the end. The divergence works very nicely in 2 dimensions, 3 dimensions, or even higher dimensions. Unfortunately, the curl is not the same way. The cross product itself is only restricted to 3 dimensions. The curl, because it's kind of based off of what the cross product does, is also restricted to 3 dimensions. We did see that we can kind of cheat it for 2 dimensions by just considering having a third component that is equal to 0. And when we took the curl, we ended up with a scalar multiple of k. And we just, because k doesn't really exist in 2 dimensions, we just kind of could consider that magnitude of that vector as what our curl could be in 2 dimensions. But that's not going to work for higher dimensions. The curl cannot go higher than 3. It just isn't possible. Of course, that's not really going to be a problem in this course. We're not really going to work with anything that is more than 3 dimensions. But it is worth noting here that the curl is kind of restricted in that way, whereas the gradient and divergence aren't. Just very different ideas. There are different possibilities we can have with these 3 operators, even though they are fairly well connected in of themselves. They do work somewhat differently. Let's return to some of the vector fields that we talked about before, we found the curl of in the last video, and let's now find the divergence. So we're doing part B when we only did part A before. What is the divergence of f? Now here, remember the divergence, we take the x derivative of the x component. We take the y derivative of the y component. Here we don't have that. We don't have a j, so the y component is 0. And then we take the z derivative of the z component. And we just add the results together. Derivative of xy e to the z with respect to x is going to be y e to the z. Obviously, the derivative is 0 is 0, so I'm just going to skip that one. Derivative of yz e to the x with respect to z is y e to the x. And in fact, I'll go ahead and factor out the y and put the e to the x first. Just because it's an easy enough step to do. We also took the curl of problem 6. So we're going to take the divergence of it this time. Same idea, we take the x derivative of the x component. We take the y derivative of the y component. And we take the z derivative of the z component. Though actually, it turns out here, there are no x's in the x component. There are no y's in the y component. And there are no z's in the z component. So all these are equal to 0. Everything here is 0. Now, unlike with the curl, that's not telling us that we actually do have a conservative vector field here. In fact, that vector field is definitely not conservative. We found that its curl was not 0. But there is going to be a kind of an implication of what that means for it to turn out to be 0. Now, we already talked about the curl of the gradient. So if we stack curl and gradient on themselves, and I'm going to go ahead and use the words here just to make it clear what we're working with. So we're taking the gradient of a little f, we take the curl of that, we already saw that equals the 0 vector. What about some combinations that involve the divergence? We could take the divergence of the gradient, we could take the divergence of the curl. Remember, both those, we basically need to plug in a vector field, and curl and gradient are the ones that output a vector field. Let's actually start with pairing it with the curl. It turns out, as long as we have our continuous second partial derivatives, which is usually the case, the divergence of the curl is always equal to 0. And that's actually fairly easy to prove. If we write out the curl of f here, where f is pi plus qj plus rk, kind of skipping all the writing it out in terms of a matrix or anything like that. Just going back to our original definition. If we then take the divergence of that, we're taking the x derivative of this first x component. Basically, we'll end up with the second derivative of r with respect to first y and then x, because now we're taking the x derivative of it. Then we have the second derivative of q with respect to z and then x. Then we do the same thing with the other two. We take the derivative with respect to y, derivative with respect to z. So here we have the second derivative of p with respect to z and then y, minus the second derivative of r with respect to x and then y. And then we have the second derivative of q with respect to x and then z, minus the second derivative of p with respect to y and then z. And note here we have the second derivative of r with respect to x and y, and the second derivative of r with respect to y and x. Those are both equal to each other because since we have continuous second derivatives, Claro's theorem comes into play. So, kind of leaning pretty heavily on Claro's theorem in these videos. The fact is that if we have continuous second derivatives, then the order of differentiation does not matter. These two derivatives are the same thing. But one of them does have a minus sign. That means they cancel each other out. Same thing happens with the second derivative of q with respect to x and z, or z and x. Those cancel out. And finally, with the second derivatives of p with respect to y and z, or z and y, those also cancel each other out. So everything here becomes 0. What that actually means is that back here, when we found that the divergence of this vector field was 0, that leaves open the possibility that there may be some vector field where this f here is actually the curl of that vector field. Now, we're not really going to go too far into that. That doesn't necessarily mean that there is one, and the book doesn't go into the conditions where that might be true. And it turns out not to be as useful to answer that question as it was when we talked about conservative vector fields. But we can actually use these kind of conditions here to actually answer those kind of questions of when is a vector field equal to the curl of another vector field. Now, if we actually look at the other combination, so here we paired the divergence with the curl. What about that divergence of the gradient? Is that going to equal 0? Well, not really. Here we're taking the divergence of the derivative of f with respect to x times I, derivative of f with respect to y times j, and derivative with respect to derivative of f with respect to z times k. Now we're going to differentiate each of these components with respect to the same one that it already was differentiated with respect to. So here, we're taking the derivative of f, or the second derivative of f with respect to x. We're adding that to the second derivative of f with respect to y. And then the second derivative of f with respect to z. Or if you want to, you could write this using the subscript notation as f sub xx plus f sub yy plus f sub zz. This doesn't always come out to be 0. In fact, it's kind of an important result when it actually does come out to be 0. This is something that's frequently referred to as the Laplacian of f. And the operator second derivative with respect to x plus second derivative with respect to y plus second derivative with respect to z. This is frequently called the Laplace operator. And where we basically say we apply this to an f by putting f on each of these derivatives. Now we could think of this as nabla dotted with nabla, because that's what we're essentially doing here. The divergence is nabla dot nabla f. but other notations, and the book actually writes this as nabla squared. That's a notation that's frequently used for the Laplace operator. But another notation that's probably more commonly seen is using a delta, a triangle here. So we can write this here as Laplace of f. The Laplace of f is the sum of its second derivatives. The non-mixed the second partial derivatives. We're not really in a position to discuss why this operator is so important, but it gets very heavily used both in partial differential equations. You might hear things about the Laplace equation, stuff like that, or also anything involving derivatives of complex functions. It turns out most complex functions, as if they are differentiable, have something about the Laplacian involved in their derivatives. And I do not want to get any more deep into that. But just be aware that this does have an actual use in some deeper calculus. Now there are a couple other possible combinations here. Theoretically, you could take the gradient of the divergence. That doesn't really have much use to it, but it is there. Instead, let's tackle problem 19. We're asking, is there a vector field on R3 where the curl of that vector field is equal to x sine y cosine y z minus xy? Is there a possible vector field where its curl is equal to this vector field? Now note that we don't have to necessarily seek out G itself. Recall from the last page that the divergence of the curl of G is going to have to equal 0 for any G that we were to plug into it. So if this G actually exists, then the divergence of this vector field has to equal 0. So let's take the divergence of this. So the divergence of x sine y cosine y z minus xy. This is actually pretty simple to do. We're taking the derivative with respect to x of our first component, x sine y, plus the derivative with respect to y of our second component, so cosine y, plus the derivative with respect to z of our third component, z minus xy. Derivative of x sine y with respect to x is just sine. That's simple enough. Derivative with respect to y of cosine of y is actually a negative sign. That kind of looks nice already. But then we have the derivative of z minus xy with respect to z, which is a 1. The signs actually do cancel each other out, but the 1 stays. So it came so close to everything canceling, but we did get 1 instead of 0. Therefore, there cannot be a G where the curl of G is equal to this. There's just no way of doing that. It's just flat out impossible. Now that's about as far as we're going to go with consequences of the divergence for now, but I do want to remind you of this restatement of Green's theorem that we found in the last video with the curl. So we essentially turned the dq dx minus dp dy into the curl of that vector field dotted with k, where we had to essentially think of that as being a three-dimensional vector field. What we're going to do is restate Green's theorem in another way that involves the divergence instead. This is going to be a little bit more complicated than it was for the curl, but it will give us something that will be similar to the other theorem that we're going to be talking about. Remember, I mentioned that this is very similar to Stokes' theorem. We're going to be deriving a formula here that will be very similar to the divergence theorem. Kind of giving things a little away with the name of that, but sometimes people also call it Gauss's theorem or Gauss's divergence theorem. Okay, so what we're going to do here, we're going to look at the integral over some curve C of f dot dr, where r, of course, is the is our curve around some D. So we have a curve C, we have some region inside of D. When we take this particular integral, this line integral, normally what we're doing is we're taking the tangent vectors and dotting them with the vectors in the vector field. Instead, let's call this t. Maybe that's a unit tangent. Instead, we could look at what we call the normal vectors. So the vectors that are perpendicular to our curve. And we were calling those capital N. For some reason here, they're going to use a lowercase n instead. This is kind of weird. They are using capital T and lowercase n, but oh well. But we're going to be looking at the vectors that are perpendicular to our curve, specifically the ones that point outward from D. So this actually takes into account our orientation. We have to be going the correct direction around D in order for our normal vector to stay pointing outward. Or if we have a hole in the middle, maybe pointing inward, just pointing away from D itself. So let's actually start putting this all together. We'll start with r of t, which in components is x of t I plus y of t j. T is going to go between a and b. So we do have some starting point and some ending point. Technically here, we do want a closed curve, so r of a and r of b are going to give us the same point, but we end up traveling along the curve as t goes from a to b. Of course, r prime of t is x prime of t I plus y prime of t j. That is a tangent vector to the curve, so that would be pointing in the same direction as t, but in order to actually get t itself, we would take this result and we divide by its magnitude. We can make it x prime of t over the magnitude of r prime of t plus y prime of t over the magnitude of r prime of t. So you just turn it into a unit vector. Now, if we were dealing with a curve in three-dimensional space, we would actually differentiate this particular expression and then normalize it as well to get the normal vector. But with plane curves, we can actually kind of skip that because it turns out that the result of that, the normal vector, will always look like y prime of t over the magnitude of r prime of t I minus x prime of t over the magnitude of r prime of t j. Which you can verify pretty easily that the dot product of t and n is always equal to 0. If we multiply those together and add multiplying those two together, the fact that we have a minus sign here and the fact that those two products will be the same thing will give us 0 overall. I'm not going to go through all the work of actually finding that vector, but it's fairly clear that these two are orthogonal to each other at all times. What's not maybe as clear is that this vector here, this expression that I've written here, is the one that's always going to be pointing outward from D as long as we parameterize C in our positive orientation. So that's actually pretty important for this. Now, if we take the dot product of f with this n, so f dotted with n, and we integrate it using the scalar line integral, so this is ds, where that ds, remember, works with the magnitude of our derivative. So this is basically equal to the integral from a to b of f dotted with n at the point t. I guess that's the way the book wrote it, but we probably should write this as at r of t, specifying that we're taking a point on the curve and then we're looking at the dot product of the normal vector and the vector field at that point. We multiply that by r prime of t dt, because that's what the scalar line integral means. Recall that when we're taking the vector line integral, what that means is just the integral over c of f dotted with t. So this is really just kind of the companion line integral. And then this one, like we said up here, turned into a curl. This one is actually going to turn into a divergence once we get to the end of it. But we kind of need to work through that. So here, this dot product, because we know what n looks like, this dot product is equal to, so f is pi plus qj. So we have the x component of f dotted with or multiplied by the x component of, there should be an n, not an r. Or wait, sorry. This is the n, that's an r. I should probably make those a little bit more distinct. Okay, so we're dotting with the x component of n. So we have this y prime over magnitude of r prime. I'm not going to denote the x and y here as being of t. These are functions of t. I'm just going to make it a little simpler to read by leaving out the of t part. Then we take the y component of f, that's q xy, times the y component of n. That's why I put a minus sign there. That minus sign is in there. We have an x prime over the magnitude of r prime. That's all going to be multiplied by r prime, or the magnitude of r prime, dt. Of course, here's part of why we want to make this a unit vector. The r primes on the bottom will cancel out the r prime on top. So we have wait. This should be a y, not an x. We have that thing dt. So already not too bad looking, but keep in mind when we have y prime dt, that's dy. When we have x prime dt, that's dx. So we can rewrite this. Let me go ahead and just put that in there. We can rewrite that integral as the integral over c of p dy minus q dx. So we have p here with the dy, we have q here with the dx. Now do note here that the p and the q are not in the normal spots that we have them. Normally we'd have p dx plus q dy. This is not the same order that we're normally used to. But we can go ahead and use Green's theorem because we are taking a line integral of a vector field. So we're going to end up with a double integral over the region inside. We take the x derivative of what's on the dy. So here, normally we'd have the q dy. Here we have a p instead. So we end up with the derivative of p with respect to x instead of q. Then we would subtract, but now we have a minus sign here, so we end up adding the derivative of the stuff that's on the dx with respect to y. So this time it's a q instead of a p. So it might seem like we end up with a very different thing here. Everything's all jumbled up, but it's because we are to derive them to be in a different position. And now, I was already talking about with this involving the divergence in some way. We recognize that what we have inside here is just the divergence of the vector field f. We don't have a plus dr dz because we're just working with 2 dimensions here. F is just pi plus qj. There's no r involved. So this is, in fact, the double integral over d of the divergence of f. And there's the way the book wrote it. So when we get to the divergence theorem, we're going to see something very similar to this. But in that case, we'll actually be working with triple integrals instead of a double integral. So this one over here will be a triple integral of a divergence. Over here, we're going to have something that we call a surface integral. But but it's going to look very similar to what we've written down here. But it is kind of interesting that if we think about the dot product of a vector field with the unit tangents, when we form this line integral, we end up getting something involving the curl. When we instead look at the normal vector fields, the things that are perpendicular to it, so we end up getting something involving the divergence. So in a sense, these are definitely companion operations. They very much do give us the other part of the same idea. Just taking line integrals that are involved with the actual tangent vectors or tangent or normal vectors, the vectors that are corresponding to a particular curve. And I'm going to go ahead and leave this video here. There's not really a lot to do with the divergence right now. The curl at least had something to do with conservative vector fields. Divergence, we can't really talk about exactly what it's going to mean for us. The book does talk a little bit about what curl and divergence mean in terms of physical situations, but those actual results and explaining why they're true actually do involve the Stokes theorem and divergence theorem that we're going to be talking about in next week. So I don't want to get too much into them right now. I'll talk about them when we can actually use the results of those theorems to actually show why they're true, rather than just throw them at you right now. But I guess you could say right now the names that we've given to these operations, curl and divergence, do kind of hint to what they're going to mean for us. Curl is going to have something to do with rotations. Divergence is going to have to do with whether or not it, especially in when we're dealing with some sort of liquid or something, whether or not things are moving into or away from a point. But that's all I'm going to say about them for right now. So stick with us. We'll get to that kind of stuff in a few sections. So I'll see you in those later videos.